So I am Aurel Page from INRIA Bordeaux, and I will teach a course on computational mathematics focused on number theory. Okay, so first things first. If you are confused about how to pronounce my name, you should think that the first two letters are actually an O. So the sound is Aurel. Okay, so what is this course about? I will talk about computational mathematics with a strong focus on algebra and number theory. So I will take a very practical point of view, like I want to provide you with a toolbox of algorithms that you can use and a few ideas from a selection of these algorithms that you can reuse, hopefully, in various contexts. So if you are more of a theory person, the goal is to provide you, to help you avoid a few common pitfalls when doing computations. And if you are more of a computation person, hopefully you will improve and widen your algorithmic skills overall. And hopefully, in any case, after the course, you will be somewhat of a computation person. Okay, so there will be 4 lectures in this course. So today I will talk about complexity and arithmetic operations. Then we'll have a lecture on algebraic number theory. And then one specialized on linear algebra and lattices. And then the first one will be various other algorithmic techniques that are useful in algebra and number theory. Okay, so first I want to start with a little introduction with some general advice for doing computational mathematics. So the first one is to actually write pseudocode. So what is pseudocode? Pseudocode is something that you don't put on your computer. It's something that you write on paper. It should contain enough information so that someone who doesn't know what the algorithm is about could still implement it. But it shouldn't contain low-level details like names of variables, loop indices, and whatever. So it's something that you make with sentences, and it should be independent of the actual programming language. So the goal of pseudocode is just to convey meaning from the algorithm, just enough so someone can implement it. And so the advice is, before you implement an algorithm of any sort, well, first, if you invented the algorithm, you should explain the idea to someone else. Actually, this someone else can be an actual person who will understand the algorithm, but it can also be like your pet or a teddy bear or whatever. The goal is just to trigger some mental process that when you explain it, it will actually clarify it in your head, and maybe you'll realize that it's complete nonsense just by saying it. And the second step is write pseudocode of the algorithm before writing the code. That will help you avoid many mistakes when programming. So hopefully you can put that into practice in the exercise sessions. Okay, so just an example of what I mean by pseudocode versus not pseudocode. So a random example. Let's take M to be an M times M square matrix. We're going to do something with it, whatever. Here's my pseudocode. Consider G the graph that has vertices, so points, and edges, so lines connecting the dots, exactly when you have a non-zero entry in your matrix. And the pseudocode says, well, find a triangle in this graph. So a triangle. So hopefully this is easy to read, conveys meaning, and when you see this, you know how you could implement it. What is not pseudocode is something like this. It's not readable. It doesn't really convey much meaning. You have no idea what's going on here. It's kind of language dependent. This is not what you want to write. Okay? Right. So when I explain algorithms in the course, I will try to give them in some kind of pseudocode. And of course, something I should also say is that the pseudocode can depend a little bit on the person who's going to read it, because for some people you'll have to provide more details depending on the background. Okay, some extra general advice about programming. So before, during your implementation and after your implementation, you should write tests for your code. So here are a few things that provide good tests. Cases that you solve by hand, just on paper, just compute them completely by hand. Cases that you can compute independently, for instance, you implemented first a slow algorithm, and then you want to implement a fast one, you can use the slow one to provide good test cases for the fast one. So in general, implementing slow algorithms is actually very useful. You should test limit cases when you're on the borders of some intervals that appear in the problem, or some set is empty, some degenerate case of some sort. You should pay attention that the tests actually exercise every part of the code, that there isn't a part of the code that is just never run during the tests. If that happens, probably that part will be buggy. And in general, when trying to think of some tests, you should try to produce tests that make your algorithm fail. That's how you're going to find good tests and find bugs in your program and fix them. Okay, some more high-level general advice. When you do computational mathematics, you should team up. So if you have more of theoretical skills, it's good to team up with someone who can do computations that you cannot. And conversely, if you have computational skills, which hopefully you will after this course, then team up with someone who cannot do the computations that you can. And you can be a bit of both, actually, depending on the person you interact with. And well, something I should add is that some mathematicians, theoretical mathematicians out there, are absolutely amazed that you can compute anything at all. So if you are able to do computations, sometimes it actually takes very little to look like a genius. So you shouldn't be afraid of approaching very strong mathematicians when you have computation skills. Here's an example of a quote by Benedict Gross, very famous number theorist. I used to use low-level languages like Fortran, Algol, and C. Now I use high-level languages like Buller, Elkies, and Stein. And if you don't know, these are people. And so, yeah, maybe you can be one of these high-level languages. Okay, so the exercise sessions will take place with the software PariGP. So I will present the software just a little bit. So it's a computer algebra software that is specialized in number theory, mostly algebraic number theory, but in a somewhat broad sense. It was originally developed by Henri Cohen in Bordeaux in the 80s. And it's currently maintained by Karim Belebas and Bilal Lambert, still in Bordeaux. I'm actually also an active developer of this software. So what are a few characteristics? It's standalone. It mostly doesn't depend on anything else. It's lightweight, hopefully fairly easy to install, and it's free software. It's composed of two components. There's a C library, which is called Pari, and a calculator that has its own script language, which is called GP. You will discover that during the exercise sessions. And the design that people have in mind in the software is that it should be easy to use with as few hindrances for the user as possible, and fast, where we aim at speed. Okay, so just a few words about the exercise sessions. Of course, we'll talk more about it tomorrow. For the participants, so we'll ask you to group by pairs to work on the exercises. Both of you should write code alternatively. And just to exercise a little bit of the advice that I gave you, so one person will write code, they will have the computer, and the other one should prepare tests on paper to test the code that is written by the other one. Okay, so you don't just sit idle on the side, and you should actually do something useful. And the exercises will be divided in 3 parts. There will be basic exercises that you should do essentially them all. There will be advanced exercises from which you should pick a selection. They will be harder, maybe implementing some of the algorithms that I presented or some problems to solve. And there will be exploration type exercises where there's no definite goal in mind. It's more explore some area of mathematics, some problem, possibly partly open, with no actually limit and end to the exercise. Okay, so here is the plan for today's lesson. So first I will give an introduction to complexity from a practical point of view, so not from the point of view of the theory of complexity, but how to actually make it useful for you in practice. And then actually a suite of algorithms for arithmetic operations in general would be the goal for today. Okay, so first complexity. So what is complexity? So the complexity of an algorithm is the asymptotic dependence of the running time of the algorithm on its input size. Okay, so it's a function of input size, and it measures what is the running time as a function of this input size. So of course it depends on the algorithm and not just on the expected output, but it doesn't depend on the actual implementation. So just a little caveat for that. Sometimes you don't specify an algorithm completely, you leave some of the subroutines unspecified, and then the complexity will depend on which actual subroutines you put in there. But once you've specified the algorithm completely, its complexity is completely determined and doesn't depend on the actual implementation. So let's make this a little bit more precise. So let me recall the big O notation for functions. So if you have two functions from the natural numbers to R, we'll write f is a big O of g if for sufficiently large values of n, f of n is bounded by a constant times g of n. Okay? And okay, so the goal of this is to absorb lower order terms and also the constants, because that's something that will actually depend on the implementation, like how many actual operations you do depends on the implementation. So for instance, well, 7n plus square root n is a big O of n. And another convenient notation is O tilde of g that will be designed to absorb a few other lower order terms, but multiplicative this time. So we'll write f is a big O tilde of g if for every epsilon, f is a big O of g to the 1 plus epsilon. So typically that will absorb logarithmic factors. Sometimes people define it slightly differently, where you're only allowed to absorb logarithmic factors and not something bigger, but that will be my definition for the course. Okay. So then the size of the input. So the size of the input always means the bit size. Okay, so the number of binary symbols that you need to represent the input of the algorithm. So simple examples, the size of an integer, it's not the absolute value of the integer, it's the actual number of binary digits that you need to write the number. So it's actually of the order of log of the number. And okay, another simple example, the size of an array of data is just the sum of the sizes of the entries, etc. Okay, so by default, when you talk about complexity, you should measure bitwise operations. So like XOR, NOT, so like the most elementary operations that processors do. However, it's very often convenient to express the complexity of an algorithm in terms of some other elementary operations that are not as low level as bitwise operations, but then you should specify what are your elementary operations. So for instance, if you have a little bit of an abstract algebraic algorithm that works in a ring R, then you will have elementary operations which will be like plus, minus, times operations in the ring. And then you may want to count the number of such operations. And then the bit complexity will actually depend on the actual ring that you choose and the operations in the cost of the operations in this ring. And well, for some rings, the bitwise cost will be bounded uniformly, won't depend on the actual elements, but for some rings the size can blow up, and then the cost of a ring operation is not actually constant. So typically integers, adding, multiplying integers is not uniformly bounded in terms of bitwise operations. It depends on the actual size of the integers. So it's slightly coarser to measure complexity in terms of elementary operations, but it's very often it's convenient. Okay, so let's do a simple example of complexity. So we'll do a selection sort. So the input is some array of whatever data of length n. Data that for which you can, with a total order where you can compare elements. And the output is the same array but sorted by increasing entries. And so, okay, here's the algorithm. So going from 1 to n, you consider the position of the minimum entries between the last entries starting from the ith one, and you swap ith one with jth one. After that, the entire array is sorted. And what is the complexity? Well, you have a loop of size n, and in each of these you do a loop of size n minus I, so the sum of these is over order n squared. So this is n squared elementary operations, and if we want to be a bit more precise, we can say we do O of n squared comparisons and O of n swaps. And so here these are elementary operations in the sense that maybe if you actually want to compare some complicated data, it's not going to cost always unit time. And also swapping, if you actually want to move the data, it may cost more than unit time. Okay, yeah, just a small note on this particular choice of algorithm. There are better sorting algorithms that have complexity O of n log n in number of comparisons. Okay, so I said that you should measure complexity in terms of size of inputs. This is by default if it's not more specified. But sometimes, especially in mathematical context, there are other parameters that are more relevant for the complexity. And then we usually use those parameters to express the complexity. So for instance, if you do numerical algorithms, maybe one relevant parameter is the desired precision of the output. And this will appear in the complexity, even though this is maybe not directly related to the size of input. Other cases could be, I don't know, for if your object is like a number field, maybe a relevant parameter will be the discriminant of the field. If it's a curve, the genus, or whatever makes sense for the actual mathematical objects. Okay, one word of warning. Sometimes there can be several ways to represent an object as input, and then, well, the algorithms available and also the complexity will depend on the actual representation, because they could have very different input sizes. So one bit of a silly example: an integer, you could write it in unary representation instead of binary. So that means well, the integer n will be an array of n ones. So of course this is extremely long, and therefore if you represent integers like this, your operations will be very fast in terms of size of inputs, but for a silly reason. But there are some actual more interesting examples. For instance, a finite group, you can represent it either by a full multiplication table, meaning you list the whole set of elements of the group, and you say for each pair of those what is their product. So this is actually a very large way of representing finite groups. But a much more compact one is by taking maybe generators of the group inside some permutation group. And the complexity of your algorithms will vary a lot depending on what is your choice. Maybe another example, if you just think of basic operations on polynomials, typically you think of dense polynomials where you write every coefficient of the polynomial, but sometimes it makes more sense to consider a sparse representation where you will only store the monomials that have a non-zero coefficient, and there could be very few of them. And again, the complexity can vary greatly depending on the type of representation that you're considering. Okay, so from a practical point of view, I will describe many algorithms with various complexities. So to give you a bit of a high-level view of those from a practical point of view, I will group them in 4 classes. So I will call an algorithm fast if it's O tilde of n, where n is the size of input, so quasi-linear. This is essentially the best you can hope for, usually. I will call it medium if it's polynomial, but not quasi-linear in the size of the input. So in practice, polynomial time algorithms can be, I mean, you can use them in many instances, but they can also get quite slow. I will call it slow if it's sub-exponential, so exponential in some power of the input size between 0 and 1. We'll see some examples where this kind of complexity actually occurs. I will call it very slow if it's actually exponential in the input size. So exponential algorithm you will usually very quickly hit a wall where you just can't compute anything anymore. And well, of course, there could be even worse complexity classes, but I'm not going to give them a special name. Okay, so thinking in terms of complexity, this can have several aspects. One goal could be you want to prove something about the algorithm that you invented. So typically proving a complexity bound is something valuable by itself. But also if you just want to do computation, it's actually useful to think in terms of complexity, just to predict the running time of your computations. If you're only interested in the output, you should still think in terms of complexity. So here is how you actually do it. You measure the running time on some small enough examples, the first few that you can get. Then you take your complexity estimate and you drop the big O, you replace it by an actual constant that matches the measured running time of your that you measured, well, in practice, like in seconds or days or whatever. And then you just use C times f of n to predict running times. And it can be very useful to know if you're going to get the answer that you're thinking about. So of course, the measured running time should be not too small to get something meaningful. If you use examples that are so small that it takes a few milliseconds, it's not going to be meaningful. So let's do a simple example. Assume that we have a quadratic algorithm with complexity O of n squared, where n is the input size. And okay, we run it with an input of size 100, and we measure 1 second. So we estimate some constant, c. And now we try with double the size. So because the complexity is n squared, we predict 4 seconds, but we measure only 3 seconds. So maybe our first example was a bit too small. We're not really in the asymptotic regime yet. Either like there are lower terms that dominate, or so we don't have the right the constant. So we re-estimate the constant, and then we try something bigger again. And now we predict, well, since it's quadratic and we double the size, we predict 4 times what we got before. So we predict 12 seconds, and here we measure 11.5 seconds. Great, we're happy, and we can predict some bigger instances that we're actually interested in. Okay, so everything here, of course, assumes that your complexity estimate is sharp and doesn't depend on some parameters that you haven't really identified. So in a simplistic way, this is how it goes. Okay, so again, one word of warning. I've sort of implicitly assumed here that we are using deterministic algorithms that just don't use any kind of randomness. Some useful algorithms and some algorithms that we don't actually know how to replace by a deterministic algorithm use a random number generator that simulates some randomness. And so we call them probabilistic algorithms. So there's a few things to pay attention in this case. Well, first, even for a fixed input, the running time could depend on the random values. So usually we try to design them in a way that it doesn't depend too much on the random values, but sometimes it's actually hard. The complexity for this type of algorithm is something slightly more complicated. So it will be expressed, for instance, in terms of expected time or with a certain probability, like with the high probability it will run in time at most some bound. And something else to pay attention, I mean, especially when you use the algorithms in practice, there can be several valid outputs sometimes. But a probabilistic algorithm maybe will just output a random one that depends on the random values that it used. So you should pay a little bit of attention to that when you use probabilistic algorithms. So it's good to know, even as a black box user, if some of the algorithms that you use are probabilistic and may return not always the same answer. Okay, so yes, and usually like in actual software, you can fix some kind of random seed that will force the running time to be reproducible and also the outputs, even if it depends on the random number generator. In terms of practical debugging and work that can be useful. Okay, so again, I said I will have a practical point of view in this course. So for some problems and algorithms, there are theoretical algorithms that are, in theory, the best, but we don't use them in practice for various reasons. Maybe the hidden constants in this big O of the asymptotic complexity are just too large for the asymptotically faster algorithm to be actually faster for real instances. Or sometimes, I mean, relatedly, maybe the algorithm is so complicated that it hasn't been implemented. It's just too difficult, or people don't expect it to be useful in practice. And so in such cases, in the course, I will mention the two complexities, like what we have for the, which best algorithms we have in theory, but which ones we actually have in practice and we actually use. Okay, one other important aspect of complexity is memory. Actually, for some applications, this is the limiting factor. Sometimes, I mean, you could, if you're able to use some computation, some specialized computers to do your computation instead of just your laptop, then you may have a lot of time, computing time. But memory could be a limiting factor because, well, memory can be very expensive, just, I mean, to buy. And so it's important to pay a little bit of attention to the space complexity. So what we call the space complexity is it's the dependence of the maximal size of the data that is used during the execution. And so again, we measure it by bits by default. But in some context, a bit more generic, we may have another kind of elementary unit that we use to measure complexity. Okay, so let's give you a simple example. So that will be in a slightly abstract context. Here we have some ring, and I'm defining a sequence by this recurrence relation. I mean, there's nothing special about it. I just wrote a random recurrence relation. And we can compare these two algorithms to compute values of this sequence. The first one is you initialize an array of length how many, I mean, the last value that you want to compute. In the first two entries, you put the starting values, and you iteratively compute the new values from the previous ones. Okay, so it has time complexity O of n. but you're storing the whole array of values, and so it has space complexity O of n ring elements. Okay, algorithm B, you just initialize a pair of elements and you iteratively update the pair so that you get one value and the previous one at each step, and you update just these two data. It has the same time complexity, so no particular difference with the previous algorithm here, but it stores only a constant number of elements instead of the whole array, so it has just O of 1 space complexity. So you should pay some attention to that, well, especially if you realize that you blow up your memory during your computation. Okay, so I'll take a break now. Other questions about this first part? Okay, so this second part will be about basic arithmetic operations in a broad sense on algebraic and number theoretic objects. So let's start with basic things. So every object that we'll consider will be built from arrays of machine integers, so usually 64 bits in modern computers. So we'll think about multi-precision integers and not just machine integers, which will be represented by an array of machine integers representing the coefficients in base B, which is 2 to the 64. We can have multi-precision reals. So I will talk a little bit about numerical algorithms, but that will not be the main focus of the course. But so I'll still mention this a little bit. So a multi-precision floating point number is represented by a multi-precision integer representing 0 point some amount of digits, and an exponent so that it actually represents 2 to the e times the other value. Polynomials, I will just consider dense polynomials in the course. I won't talk very much about sparse representations. So polynomial will just be an array of numbers or other types of coefficients representing the coefficients. And then vectors, matrices are arrays of numbers, arrays of vectors, etc. Okay, so first basic operation, addition of everything you can think of is linear, so it's a fast algorithm. And just as a warm-up, let's look at the way we would write the pseudocode of that. So we have these two n-digit integers, and here would be the pseudocode of that. Compute the n+1 digits of a plus b starting from the least significant ones, so coefficients of small powers of b. And at step I, you compute the ith coefficient by the sum of the coefficients plus the carry. So just, this is of course a very simple algorithm, but I just want to emphasize that when you write pseudocode like this, it's good to, for us here, mention the carry. This is something that you should pay attention to when you implement it, so it should be mentioned in the pseudocode. Okay? So every step is just O of 1 elementary operations, at most n+1 steps, so this is O of n time complexity. And we only need to store C in addition to the output, so excluding the output, this is O of 1 space complexity. Okay, more interesting is multiplication. So in short, integers and polynomial multiplication, we have fast algorithms for this. So quasi-linear. We'll say a few more about the details of the lower order terms. Matrix time vector multiplication. Basically, there's nothing better than the actual formula for matrix times vector multiplication. It's as fast as reading just reading the matrix. So it's just linear. And matrix times matrix multiplication is more interesting. So for this, we have what I call medium mediumly fast algorithms, so polynomial but not quasi-linear. But still, as you will realize, if you have several matrix times vector multiplication with the same matrix, then it's good to actually do them all at the same time in a matrix times matrix multiplication. Okay, so let's go into a bit more details of these algorithms. Okay, so I will consider integer multiplication and then matrix multiplication. So let's start with the basic one, Schoolbook, just applying the most elementary formula. So the multiplication of two n-bits integers will be you initialize the digits of a times b, and well, just pay attention here. The pseudocode here pays some attention to how many digits you should have. Just this is something that's easy to forget when you implement it. And then for every pair of coefficients, you just add the product to the corresponding coefficient of the product, and then propagate the carry. So we perform a constant number of operations for each pair of coefficients of the input. So the total complexity is quadratic over n squared. And so this is only what I call medium. And so it's not so good, and we would like to improve on that. Okay, so I will not go into the low-level details of fast integer multiplication. So to simplify, I will consider multiplication of two polynomials with complex coefficients and of degree which is a power of 2. So pay a little bit of attention that here I'm asking the coefficients to be complex numbers. So I'm actually reducing multiplication of numbers to multiplication of numbers. So you have to be a little bit careful here. But for now, we will just assume that we know how to multiply complex numbers, and we'll use that to multiply polynomials. Okay, so what is the ID? And this is a type of ID that will come back in other situations. We want to evaluate the product, each of the two inputs at two endpoints, which is the degree of the product. Then we multiply the evaluations, which, this is there will be just two basic multiplications to do. And then you interpolate to recover the full product. And if you do it just with random evaluation points, you don't gain anything. To gain something, you need to choose very special evaluation points. And the good ones to use are 2 to the kth roots of unity. That's why I picked C here, to actually have these roots of unity. And so we will be able to use a divide and conquer method in the following way. So if you have your polynomial, one of the two input polynomials P, you can separate it in even part and odd part. If you think in terms of the algorithm to do that, this is just changing this is just permuting the entries. Like this is the 0, 2nd, 4th, etc., the even coefficients, and this is the odd ones. So if you want to separate here, this is just permuting the entries, putting the even ones first and then the odd ones. Then if you evaluate this at 2 to the kth root of unity, well, okay, you just get the evaluation, but the remark here is that these two polynomials have degree that is halved compared to the initial ones. And because we squared the root of unity, we also halved the order of this root of unity. So you'll have half as many evaluation and interpolation points. Okay? And so we can put these together into what is called the fast Fourier transform. So the fast Fourier transform is from P. You want to evaluate at all the P of zeta. And maybe I should say, why is it called the fast Fourier transform? Where if you write down the formula for the sequence of P of zeta, where zeta are all the roots of unity in terms of the coefficients of P. This is the same as looking at the array of coefficients and taking its discrete Fourier transform. So like it will be sums of powers of roots of unity. So this is really a Fourier transform. Okay, so what's the algorithm? You first compute P0 and P1. So as I said, this is just a permutation of the coefficients. Then you call the algorithm recursively on half the size twice, so on the left side and on the right side. And then you recover all of the P of zeta. Well, each of the Pi's of zeta prime will contribute, according to the formula displayed before, to 2 values of P of zeta, corresponding to the 2 square roots of zeta prime. So this recombination will just, again, you will repermute the vectors and multiply by a suitable root of unity. So how do you analyze this complexity? So this is typical of divide and conquer algorithms, where you split the problems into smaller ones, and then you recursively solve the small ones, and then you merge the solutions. So I will look at the function of n, and actually it's easier to look at it as a function of k, where n is 2 to the k, in terms of complex number of operations. And it satisfies a certain recurrence. So the time for size n is, well, twice time for size n over 2 because of this recursive step. And then if you inspect these 2 steps, you can see that they are simply linear, just permuting the entries or just multiplying by some fixed value. And so in terms of the sequence, it looks like this. And if you do then a little bit of just analyzing recurrent sequences like this, linear recurrent sequences, you'll realize that the solution is simply UK, which is a big O of k times 2 to the k. In other words, T of n is O of n log n. So one subtlety here is that we've counted complex number operations, which is not really allowed because we're actually trying to multiply numbers, and for that we are using multiplication of numbers. Okay, so it's actually circular. And so, oh yeah, sorry, I should have mentioned that I mentioned evaluation and not interpolation. But because this evaluation, it can be interpreted as a Fourier transform, and you know that Fourier transform is essentially an involution, like the inverse is essentially the same, then you can also do the interpolation in the same amount of time. It's actually essentially the same operation. Okay, but so the subtlety is that we need to take into account the cost of the complex number operations at the suitable precision. So this is, again, a little bit an example of what I was mentioning before. If you count just the basic ring operations, you may be missing something from the complexity analysis. So there are 2 ways to solve this. Either you actually go into the details of what is the necessary precision to recover actual, say, integers at the end, and you estimate recursively again how much it costs to multiply these complex numbers at the right precision. And the other option is to work in suitable finite fields to avoid complex number operations. But again, you will reduce to some, also to some other multiplication. So you also have another estimate to do here. So this was the work of Schönagel and Strassen, which gave an algorithm that, in terms of bit complexity now, if you put everything together, it has complexity. So remember, n is the number of bits of the integer, really size of input, n log n times log log n. And this actually was the best known for quite a bit of time. So this dates from the 70s, but very recently, Harvey and van der Heuven, with a much more complicated algorithm, managed to get this down to actually O of n log n without the extra log log n factor. And this is actually a lot of work. But what I should also add is that this algorithm is actually used in practice. It's implemented, and we can actually reach sizes of integers where it's useful. At the moment, this new algorithm has an enormous constant and works for sizes of integers that we can't even write down on a computer. But who knows, maybe with further refinement, it may actually become the best algorithm in practice in the years to come. Okay, so I will now pass to matrix multiplication. So so to simplify, I will just consider multiplication of square matrices of the same size. Or again, I should have said for the integers, again, I talked about multiplication of integers of the same size. If you multiply a long integer by a short one, the complexity will vary accordingly. Same here for matrices. If they are not of the same size, you can cut them by blocks and use what we will describe here for square blocks. But for simplicity, I will just explain what happens for square matrices. Okay, so what is the Schoolbook algorithm, the one that comes just from the linear algebra formula? So it's the following. You just initialize the coefficients of the product. And for every triple ijk, you add this product to the ijth coefficient of a times b. So each of these is a constant number of operations that you do for every triple of coefficients. And so the total running time is O of m cubed. And again, if you think in terms of size of the input, this is n to the 1.5. So it's not quasi-linear. The exponent is not 1, but it's not actually that far. And it is currently an open problem whether or not you can obtain something quasi-linear, which would mean m squared in this case. So this we don't know if it's possible to achieve. So a little bit of a comment here. So we will describe faster matrix multiplication algorithms, but they don't reach quasi-linear. But even if you had quasi-linear algorithms, what you should think is that if you have the same object that you can encode either as a matrix or polynomial for some reason, it's usually better to encode it as a polynomial just because it will be smaller and all operations will be faster. So even if we have somewhat fast matrix multiplication algorithms, just because of size, a matrix is a somewhat inefficient representation. Okay, so faster matrix multiplication. So this is an idea that goes back to, again, Strassen in the 60s. So Strassen gave an explicit formula, which I'm not going to write here explicitly. It's a bit of an ugly formula, but completely explicit, for the product of two 2x2 matrices. So again, if you think of the basic, the schoolbook formula for 2x2 matrices, you will have exactly 8 products in this formula. That's the m cubed that we saw earlier. And just for 2x2 matrices, fixed size, he was able to write down a formula with only 7 multiplications. But the most important point about this formula is that it was valid even if the coefficients are not commutative. You're not allowed to swap the products in the coefficients. And why is this important? It's important because we want to recursively use this on matrices of half the size. And well, as you know, products of matrices don't commute. So you have to have this property so that you can actually do this recursion. So what is Strassen's algorithm for multiplying in size to 2k? You subdivide your 2 input matrices into, each 4 blocks of size halved. Then you compute the 7 Strassen products recursively, and then you recover the product. So in the process, this actually involves many additions, like a lot more than in the usual textbook formula. But they don't actually, as we'll see, the addition, it doesn't matter that there's a lot of them. Okay? So let's analyze this. So again, we have this divide and conquer type algorithm where we divide the size of the input and we call several times the same algorithm recursively. So we'll analyze it again using the same type of recurrences as before. So the number of operations satisfies the following recurrence. So for size m, we will use 7 multiplications of size halved, plus maybe a large number, but it doesn't matter, of additions of matrices of size essentially m times m. Oh, this should be an, actually this should be an m squared, I'm sorry. But again, it doesn't actually matter. So this is the additions and manipulation of data that you do. And again, you end up with a recurrence like this, and what will actually matter in this is the main term will be just this, and if you solve it, you realize that the solution is UK is 7 to the k. So if you think what we had before, like the schoolbook algorithm, that would be, here we would get the cube of 2 to the k, so that would be 8 to the k. This comes from the 7 multiplications. So what do we get from this? So if we go back to the actual size of the matrices in general, you'll get a complexity that is m to the log 7 over log 2. If you just replace this 2 to the k by m. And so this is slightly smaller than 3 here. And so if you think in terms of size of input, we got slightly closer to actual quasi-linear, to O of n. So this 1.5 became 1.4. So this, when it was described, people thought that it would never be used in practice, but actually it's already useful in very realistic sizes of matrices. So most software that you will use and multiply matrices will actually use this fast matrix multiplication. On the other hand, there's been some improvements of this technique in a much more refined way. And the currently best known, and I think this is from the maybe 2019 or something like this, we can get the exponents, well, somewhat closer to 2, but still quite far. But essentially none of the better algorithms of this type are actually useful in realistic size matrices. Okay, so very quickly, so this is not as interesting. I mean, you can essentially reduce division to multiplication with some techniques. So integer polynomial division will have the same essentially asymptotic complexity as multiplication, and same for matrices. I mean, we'll say a bit more about it when we talk about linear algebra. Again, the GCD, so this is not as obvious, but I'm not going to describe the algorithms involved in this. You have GCDs of polynomials or integers. This is also quasi-linear, so it's same asymptotic complexity as multiplication. And I'm going to talk a little bit about a variant of the GCD, which actually is quite useful and which is called the resultant. And I think maybe this is a good place to make a little break. Yes, so then, okay, that was... Okay, so GCD, again, there's an interesting algorithm here, but I'm not going to describe it, which achieves computation of the GCD in quasi-linear time. Actually, if you know, well, you may know the Euclidean algorithm to compute GCDs, and this doesn't achieve this fast complexity. It would be quadratic. I want to talk a little bit more about its variant, which is the resultant. So the resultant is somewhat similar to, related to the GCD, but very useful too. So it takes place in a ring, and you have two polynomials in this ring. The resultant of the two polynomials, which I will sometimes specify the variable with respect to which I take the resultant, just because it's very often useful to take resultants when R itself is a polynomial ring with other variables, or other polynomial variables. And so here are, a selection of the basic properties of resultants. The resultant has a polynomial expression in terms of the coefficients of P and Q. So in particular, if you see P and Q as being not polynomials over R, but over another bigger ring, or even if you apply a ring morphism, the resultant will be the same, or will be the image under the ring morphism. So this is an important property. Then something that is useful to think about how resultants operate. If you are over a field and your polynomial P factors completely over that field, the resultant is the same as, some fudge factor that comes from the leading coefficient, but mostly it's the product of evaluations of Q at the roots of P. So we'll see in a moment how, what roles this plays. Another important property is that the resultant is in the ideal generated by P and Q. So it's an element of R, so it doesn't have the X variable anymore, but it's in the ideal generated by R and Q. So you should think of the resultant as something that eliminates the variable X from the two polynomials. Okay, and also, it's essentially symmetric in P and Q. P and Q don't actually play a special role. This is a very asymmetric expression, but really the resultant is essentially symmetric. So there are several applications of resultant, but let me mention two of them. One of them is that it allows you to compute with numbers not represented by the number itself, but represented by a polynomial at which the number vanishes. So that will be, that's useful when you think in terms of algebraic numbers, for instance, but can play a role in other contexts. So for instance, why is the resultant important for that? If you think about this resultant of P of X and Q of Y minus X, so I take the resultant in X and I have this extra polynomial variable Y. So think about the previous expression I had here, second polynomial evaluated at all the roots of the first one. So this resultant will be the product of Q of Y minus alpha, where alpha is a root of P. And what are the roots of the resulting polynomial? Well, you've for each alpha, you've shifted the roots of Q by alpha. So the roots of this resultant as a polynomial in Y are exactly the sums of the roots of P and Q. So without actually using the roots themselves, you can use a resultant to represent the sum of these roots inside of a polynomial, by a polynomial that vanishes at those. So that's very useful, for instance, in algebraic number theory. And as I mentioned, because the resultant has this property of being in the ideal generated by the two polynomials, it's useful in elimination when you think of solving algebraic systems. You can think of it as a projection. And just like the GCD, there are fast algorithms to compute resultants. This is actually quasi-linear. So if you think, for instance, in terms of applications to algebraic systems, it's very useful because it performs some kind of elimination in quasi-linear time. If you think of other methods to do elimination, such as Grobner bases, they have really terrible complexity, like doubly exponential. This doesn't even fit in my classification. Okay? So this is a very useful tool. Okay, another basic useful operation is exponentials in general. So two basic type of exponentials. Well, the natural one would be exponential over c, as in the actual exponential function. This is, numerical function. So for this, we have an actual fast algorithm, which is quasi-linear in the size of input and also in the desired precision. So I won't say much about this. In an algebraic context, we can ask for exponentiation in the sense of taking an element in the ring and raising it to some power, an integer n. And that's what we would call exponentiation here. And so, well, okay, this would actually even make sense in a group, simply. I mean, here I'm talking in general about operations in rings, but this also makes sense in groups, and this algorithm also works in groups. So the algorithm is repeated squaring. You just think of n as being written in a binary, in base 2, with coefficients 0 and 1, and you simply expand this exponentiation to the n in the following form. Just raise a to the first, well, to the most significant coefficient, square that, multiply. So here, multiply by a to the n and to this coefficient. This coefficient is just 0 or 1. So this is just either you multiply or you don't multiply by a. Square, multiply, etc. And how many operations do you perform? Well, as many times as the number of digits of n, you will do one square and maybe one multiplication. So this is a fast algorithm. It uses only just O of n operations in R. So again, you have to pay a little bit of attention when you think of this algorithm in rings where the entries can grow. So in finite fields, that will be essentially the whole story. If you think about integers or rationals or whatever, you have to take into account the actual growth of the output in the complexity. Okay, so that's for exponentials. So we have a fast algorithm, but more interesting is the converse operation, logarithm. Okay, so again, over C, so now I'm thinking of the logarithm function in C. So we have again a fast algorithm, just quasi-linear in size of input and precision. And over ring R, what I will call logarithm will be the discrete logarithm problem. So you're given a and a to the n, and you're supposed to recover n. That's what we call the discrete logarithm problem. Again, it would make sense in any group. Doesn't have to be part of a ring. But I will talk about what happens in finite fields specifically here. So if you consider an n-bit finite field of size q, so q is approximately 2 to the n, we have a slow but still sub-exponential algorithm for performing that. Okay, so it's sufficiently fast that you can actually use it in practice. I mean, this you can actually implement, and it's actually much faster than what you could think in terms of naive algorithms. But it's still a difficult task still is the topic of much research. And even better, so there are really two parameters in the size of your finite field. There's the characteristic, which is a prime p, and the degree of the field extension, which I'm calling E here. And if the characteristic is actually very small, then we have something that gets very close to being polynomial. So very close to being what we could call a mediumly fast algorithm. So I didn't write here the actual formula for the complexity just for simplicity, but you should think this as being almost mediumly fast for very small characteristic. Okay, another interesting problem both for integers and polynomials is the factorization problem. So factorization is you take an integer or a polynomial and you want to write it as a product of primes or irreducibles. Actually, you could make sense of that in well, any ring where you have unique factorization into irreducible, you could ask for this problem. So I will go into more details, but in short, over the integers, it's hard. We have slow algorithms, sub-exponential time algorithms. And well, actually, the fact that we have, oh yeah, I should have said that maybe when I talked about discrete log already. So exponentiation is fast, and in some cases, we don't really know how to do discrete log quickly. So we can try to do crypto based on that. And similarly here, we have multiplication and that we can do quickly, and factorization that we don't really know how to do quickly, and so we can base crypto on that. But all of this is only valid for classical computers. I should have said that at the beginning of the course. I will not mention quantum algorithms in the course, but both discrete logs and factorization of integers are two problems that we know how to solve in polynomial time, so with a medium algorithm on quantum computers. Yes, this is still an important point, but I will mention quantum algorithms very little in this course. Since, well, the focus is on algorithms that you can use in practice, and we're very far from actually building quantum computers that can solve these problems faster than classically. Okay, so for integers, slow algorithms, but still sub-exponential. And for polynomials, over basically all the fields that you will think about in well, most of your time, reals, complex numbers, or finitely generated fields, so finite fields, finite extensions, I mean transcendental extensions of finite fields with finitely many variables, say number fields, and also finite transcendental extensions of number fields. We have polynomial time algorithms to factor polynomials over these. So these reasonably usable algorithms. So I will go into a little more details of this. So factorization of integers. So the general factorization problem is hard, but it's interesting to know like which special cases are actually easier than other ones. So we consider n-bit integers, so recall that little n is essentially log of n. So some easy special cases, detection of powers. So if your integer is a power of another integer, you can find that very quickly, actually in quasi-linear time. Detection of primes. So if you're given an integer, actually finding out whether or not it's prime, this can be done also in polynomial time. So this is, I think, the best currently known complexity. The algorithm that realizes this complexity is not actually the one used in practice. And for practical problems, there are two approaches. Either you just want to convince yourself very quickly that the integer you're considering is prime, and then you will use very fast tests that could potentially fail, but only on very few integers, like so few that you will never see them in your life. Or you could try to run an algorithm that produces a proof that the number is actually prime. This is much harder, but we have, essentially the best algorithm to do that is based on elliptic curves, called elliptic curve primality proving algorithm, and it has polynomial time complexity based on some conjectures, I think. But you can actually use it in practice if you want an actual proof of the primality of an integer. Okay, so that's the two easy cases. Now let's consider the actual hard case where you don't have a power or a single prime. Okay, so the first algorithm that you could think of is just trial division. Try dividing by all the primes up to square root n. Okay, so why square root n? Because if you have at least two primes that divide your integer, then at least one of them will be less than square root n. And this belongs to the very slow class of complexity that I mentioned. This is exponential. Still, you could think of the slightly simpler problem of just finding the small prime factors of your integer, and then it would be exponential, but just in the size of the primes that you want to find. So this could still be useful. But actually, there is a better algorithm even just for finding prime factors up to a certain bound. So if you want to find all prime factors of n that have at most b bits, so at most 2 to the b, then we have a slow algorithm, but still, sub-exponential, better than the just trial division, much better. And so the complexity is essentially exponential of square root of the number of bits of the prime factors that you want to detect. So this means that using this, there are still quite a few numbers that are actually easy to factor. If you have a lot of prime factors that are small, like small enough that this algorithm will actually find them, and then one very large prime, once you've eliminated all the small prime factors and you're left just with a very big prime, you can factor that in polynomial time because you can identify primes in polynomial time. So there are many integers that are easy to factor. What we believe is that the hardest case is just a product of two very large primes. And then, in general, for complete factorization of n, the best algorithm that we know is again, slow algorithm with a sub-exponential complexity. So essentially exponential of 1/3 of the bits of n. What I should add is that these two algorithms are actually implemented in practice and really useful. And one interesting aspect is that this one is actually used for that one in the course of the algorithm. And in this domain, there's a frustrating open problem, which is that we don't know how to find just the largest square factor of a number faster than just completely factoring it, which, when you think about it, is a bit outrageous, not being able to even test whether an integer is square-free or not. Actually, as you will see, it's, for polynomials, you can do complete factorization in polynomial time, but you can also do this square-free detection even faster than complete factorization. Okay, so I won't go into the details of these. Maybe we'll mention some ideas involving those, but a bit later in the course. Okay, so let's go to polynomial factorization now. So, as I said, the most easy part of factorization is square-free factorization. So every polynomial, or this is actually true in every ring with unique factorization. Any polynomial can be written as a product like this, product of polynomials to various powers, where each of the blocks here is square-free. If you think maybe in terms of, if you think in terms of irreducible, this is quite obvious. And what is nice here is that because we have these derivative 2, for polynomials, which we didn't have for integers, satisfying the property that if you take the GCD between p and its derivative, then it just decreases the exponents by 1. You can use this as a building block to have an actual fast algorithm to compute the square-free factorization, quasi-linear in the size of the input. So this is very good. And also, for polynomial factorization, I mentioned these finitely generated fields. This works over just any ring. Well, I guess, okay, technically speaking, or any characteristic 0 field, but you can do something special for a positive characteristic, which I didn't mention here. Okay, so I talked about factorization over our arbitrary finitely generated fields. I'm not going to describe each of the pieces of these algorithms. I just want to describe in a bit more details how to do it in finite fields, because I think the ideas involved in that are useful in other contexts. So I'll give a bit more details here. So because we have the square-free factorization first, I will assume that my input is square-free. And I want to separate P into a product, so what is called the distinct degree factorization. So I want to write it as a product where each of the Pi is not necessarily irreducible, but it's a product of irreducible factors that have all degree I. Okay, so all the irreducible factors of P1 have degree 1, all the irreducible factors of P2 have degree 2, etc. And for that, we'll use the one basic property of finite fields, which is that, oops, there's something missing here. There should be an x minus alpha here. So x to the q to the I minus x, this is the product of the x minus alpha, where alpha is in fq to the I. And what this means is that you can obtain, this is actually slightly wrong. Okay, actually, by taking this GCD, you will get the product of the PIs, of these factors up to I. You have to tweak this a little bit to get exactly PI. Sorry, there's a typo in this slide. But the basic idea is that using these polynomials and this type of GCD, you can extract the distinct degree factorization. And here, this polynomial x to the q to the I minus x, this has very large degree. So you don't want to actually write down this polynomial. But you can do the same computation because the GCD is the same when you reduce the left polynomial mod p. You can compute exactly the same thing by taking x modulo p and raising it to the power q to the I every time mod p. And because of fast exponentiation, this you can do in polynomial time. Instead of, you don't actually write this full polynomial. Okay, so once you've raised x to the q to the I mod p, then you just subtract x and you take these GCDs and, well, it's just not just pi, but you combine them in the right way and you get the distinct degree factorization. Okay, so that's the first block. And so once you are at this point, you can assume that all the irreducible factors of your polynomial have the same degree. So we'll assume that we have a square-free polynomial p1 times pk. So these are distinct irreducibles. And they all have degree exactly d, fixed degree. And now the technique to do this factorization will be an actual probabilistic algorithm. And this is something that we don't know how to do in polynomial time without using randomness, without a probabilistic algorithm. So the way to do it is to think about this ring, fq of x modulo p. So even if you don't have the factorization, you can think of this ring as follows. By Chinese remainders, it will be a product of fq of x modulo the irreducible factors. And so it will be a product of k copies of the same finite field of size q to the d, and d is something you know at this point. And so if you take an arbitrary element of this ring and you think about it as an element here, and you raise it to the power q to the d minus 1 over 2, then, well, when you square that, you get 1 by properties of finite fields. So each of the components of this product is a plus or minus 1. And if you take a random element in R, you will actually, I mean, each of these signs will be plus or minus 1 with probability 1/2 all independently. And so if you take a random element in R, and you just subtract 1 so that this will be a bunch of, subtract 1, so minus 2 or 0. And you compute the GCD with P, then this is going to extract exactly the product of the factors where you got a 0 here. So with large probability, you will find a non-trivial factor of P by doing this. And using several random elements, you can actually get the complete factorization. Okay, so this is our first example of a medium, a polynomial time algorithm that is probabilistic and that we don't know how to do deterministically. Maybe still one thing to mention here is that, yes, it's a probabilistic algorithm, but the output doesn't depend on the randomness that was used for the computation. The output, there's only one valid output. It's this product of polynomials. Okay, so it's a probabilistic algorithm, but in a mild way that is usually not very annoying. And on this last algorithm, I will end today's session. And thank you. And well, you can ask some questions if you have. Thank you.